Hi, in this video we are going to talk about the traveling salesman problem, or the so-called TSP. So let's get started. The problem itself is that given a list of cities and the distances between each pair of cities, and what is the shortest possible route that visits each city exactly once and returns to the original city. It is an NP-hard problem in combinatorial optimization, because if we have n cities, then there are n factorial permutations available, so brute force methods cannot be used. And it is possible that the worst case running time for any algorithm for the traveling salesman problem increases exponentially with the number of cities. There are two important expressions as far as the traveling salesman problem is concerned. First is the Hamiltonian path. So what is a Hamilton path? A path in an undirected or directed graph that visits each vertex exactly once. So if we visit every vertex exactly once in the graph, then it is called a Hamiltonian path. The Hamiltonian cycle is a bit more difficult because it is a Hamiltonian path that is a cycle, so the starting vertex and the end vertex is the same. So here for the traveling salesman problem it is very similar to the Hamiltonian cycle, but here we are looking for the shortest path Hamiltonian cycle basically. So of course for a graph there may be several solutions in the sense that several Hamiltonian cycles can be constructed, and we are looking for the one that has the overall shortest path, so the sum of the edges will be minimum. Okay. So for example, let's consider this situation. We have the A, B, C and D vertices. We have several edges with edge weights. Basically in this graph, we are able to form two Hamiltonian cycles. The first one is this, going directly from A to B, then from B to D, then from D to C, and then from C to A. The total cost is going to be the sum of the edge weights, so 1 plus 3 plus 1 plus 5, which is going to add up to 10. But there is another solution, this one. It's going to be a valid Hamiltonian cycle if we go from A to B, then from B to C, then from C to D, and then from D back to the starting vertex. And it's very important that for a Hamiltonian cycle, the starting point and the end point have to match. The total cost in this case is 1 plus 2 plus 2 plus 1, which is equal to 6. So in this case, because we are looking for the shortest path Hamiltonian cycle, in this case, this is the solution of the traveling salesman problem. It could be the solution too. Okay, it's going to solve the problem, but the total cost is 10, and we are able to find better solution. So this total cost 6 is going to be the solution for our traveling salesman problem. So basically, this is the problem we are going to consider. And let me tell a few words about the algorithm. The most direct solution would be to try all the permutations. This is the so-called brute force approach or the brute force search. But it's going to take ordo n factorial running time, which is of course impractical even for 20 cities. Another solution is the dynamic programming approach, the so-called HELD-CARP algorithm, but it is not that fast too. So the principle, and basically that's the basic of heuristic and meta-heuristic algorithms, that we just want to get an approximate solution. It doesn't need to be the best possible, because we know for sure that it is a very hard problem to solve. And of course, if the problem is hard, of course there won't be any fast algorithm that's going to solve it. So we come to the conclusion that, okay, we would like to solve this problem approximately fast. Then what can we do? Okay, so we are not going to look for the exact solution, the best possible. We are looking for the approximate solution, and basically it can be done with Monte Carlo based simulations, such as for example the simulated annealing, or we are going to talk about genetic algorithms. Genetic algorithms is one of my favorites, and it's going to solve the traveling salesman problem like a charm. Okay. So there are several methods for solving the traveling salesman problem, as I said earlier. For example, the random tour. We choose a random tour by random. So, of course, it's not so efficient. What about the greedy search? That we always choose the next nearest city possible. Of course, that's not good. For Dijkstra's algorithm, which is a greedy algorithm, it turns out to be good. But in this situation, the greedy algorithm is not going to be the best. We have this so-called two-opt solution that we generate a random tour and we take a route that crosses over itself and reorder it so that it does not going to cross over itself. So if the tour overall distance cannot be enhanced with swap of edges, then we terminate our algorithm. Sometimes it works, sometimes it does not. But the simulated annealing is going to work fine. It can avoid local minimums. It is like Metropolitan Hastings algorithm, so we allow non-optimal sub-solutions too with given probability. That's why this is not a greedy algorithm. The greedy algorithm is not going to allow non-optimal sub-solutions. It's going to take the best possible. And that's why it's not going to be okay, because computer scientists and mathematicians came to the conclusion it is quite counterintuitive, but sometimes allowing non-optimal sub-solutions is going to make the final solution better. So, what's important that we allow non-optimal sub-solutions with given probability. For other algorithms, this probability is constant, but with simulated annealing, the probability is changing. At the beginning, we have a high temperature, we call this T parameter temperature, and as the T decreases in the course of the algorithm, the probability decreases too. What probability? The probability that we allow non-optimal sub-solutions. So basically it means that we reject bad solutions as the temperature falls. And what's very counterintuitive, that this algorithm is going to work very, very fine. So, accepting worse solutions is a fundamental property of meta-heuristics because it allows for a more extensive search for the optimal solution. And basically for genetic algorithms, we are going to see that that's what's happening in the background. So we initialize T, the temperature parameter, to be high at the beginning, and then allow it to slowly cool, which means that we keep decreasing the value of the temperature as the algorithm runs. And while this temperature variable is high, the algorithm will be allowed with more frequency to accept solutions that are worse than our current solution. So basically, it is allow bad steps. And I think that this is what's quite counterintuitive with these kinds of meta-heuristic algorithms, that we get used to greedy algorithms. Dijkstra, it's going to take the minimum distance. For spanning trees, Prim's Yarnik algorithm is going to take the minimum edge weight and so on. Here in this case, we are not going to take the best sub-solution. And I think that it is quite counterintuitive that in the end, it's going to give very, very good results. So it gives the algorithm the ability to jump out of any local optimums it finds itself in early on in execution. And we keep select edges at random. This is why it is similar to Monte Carlo algorithms, and keep swapping them with a given probability. By the way, what does it mean that local optimums? Basically, a local optimum is what we have discussing here, that it is a solution, but not the best one possible. Because we know for certain that we are able to find a solution with total cost 6. And basically, meta-heuristics is going to say that, okay, we know for certain that finding this exact solution is going to take very, very long time. We just want to get an approximate solution, and maybe the meta-heuristic algorithm is going to allow this total cost 10 as the solution. It is not quite far away from the best solution, which is the 6, but it is approximately good. And okay, you may pose the question that, okay, if we have an algorithm that's going to calculate the exact solution, why is it good to end up with a suboptimal solution? For example, this total cost 10, when the total cost is 6, we are able to calculate it. Because if we want to make this traveling salesman problem, for example, and it is quite common in practical applications, for example, for 100 cities or 200 cities, then finding the best solution, the exact solution for the traveling salesman problem is going to cost a lot. What does it mean that costs a lot? It's going to take a lot of time to calculate it exactly. And that's why sometimes we come to the conclusion that, okay, we don't want to find the exact solution, total cost 6. We are good, we are totally fine with this total cost 10, but we would like to find this solution that what's going to be the order of the cities that we have to visit. And as I said earlier, there are several applications of the traveling salesman problem in logistics, for example. How to route vehicles in order to optimize that it's going to make the shortest path possible and it's going to visit every city exactly once. And of course, it's going to come back to the same city as it has started. Okay, so that's all about the traveling salesman problem. Thanks for watching.